Alright, in this one we're going to do a bit of a concept exploration for you Calc BC students. So if you're in Calc BC, grab yourself a notebook, a pencil, or a pen, if you're so bold. Or if you take notes on the computer somehow, do you. I'm not going to judge. However you'd like to write is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're, like I said, investigating Euler's method. It's a nice method. It's a numerical approach method to approximate the particular solution of a differential equation. Now, we're mostly going to be using this to get values, but Euler in his time would have used this method, for example, to roughly but accurately plot the positions of maybe a rocket, if he were around during this time. Of course, rockets didn't exist when Euler was alive, but in situations where we understand the derivative, although not the solution to the differential equation, not the original positional equation that defines the positions of something moving, we're able to use Euler's method to approximate. And you might be familiar with approximation via the tangent line. In fact, you can see that there's kind of a tangent line here that's drawn. And we use this to say, okay, it's exact at a specific point, and it's pretty close as long as we're pretty close to this point, x0 or whatever you want to call it. The further away we go, the further the tangent line deviates from the exact solution curve, which is good right here, this sort of curviness. So what Euler said, his method proposes, is to sort of update your tangent line along the way, right? So it's sort of like it's like derivative powered GPS that kind of lags a little bit, right? Or like if you were blindfolded and someone were just telling you, like, take one step forward and then turn a little to your left or turn a little to your right and take another step forward, and they'd be trying to get you to follow a curve, right? That would kind of be the best method in steps like that. And so, Euler, I'm not sure if that's what he looked like, but he was brilliant, absolutely brilliant. Next to Gauss and Archimedes, absolutely the best mathematician of all time. Oh yeah, Newton's up there too, let's give him some props. So let's see how this method works. We're given a differential equation. Again, we understand the behavior of a system in terms of its movement, so we kind of understand how fast it's moving, but we don't really understand the exact curve that defines the motion. So what we're going to do is we're going to approximate the function value of this mysterious y function at x equals 1. We're going to approximate that starting off with x equals 0 and then sort of progressing forward with a tangent line from there. So here's a way to do that. We're going to have our x values. We're going to have our f of x values, or you can put y if you'd like. And we're going to have our, that's not really an equal sign, is it? And we're going to have our derivative dy dx, which is going to be updated. The slope of the tangent line is going to sort of be updated as we progress forward. So let's start with what we know. We know that f of 0, for example, is 2. And then we can calculate what the slope would be there so that we can write a tangent line at that point. So we're going to say that dy dx equals to 4 times 0 squared plus y. So our derivative at that point is 2. Therefore, we can make an equation of tangent line, y minus 2 equals 2x minus 0, or if you just want to call it x, that's fine. Now, what do we do with this tangent line? Well, we need to move forward along the tangent line, but we're not going to go all the way to x equals 1, because we know that that would have quite a large gap, right? It'd have a larger gap. If we update the tangent line at 0.5, then we can use sort of a new quote-unquote tangent line. Notice that it's not an actual tangent line because it's not tangent to the curve, but it's sort of parallel to the tangent at that curve. So it's using the appropriate slope at that point in order to determine how we should move next. This is equivalent to someone giving you the instructions to just move a little to the left or turn a little bit to the right. So let's try to use 0.5, and this is where it becomes useful to use a tangent line, because we don't know what f of 0.5 is, but if we use this tangent line to say that y minus 2 equals 2 times 0.5, then we can get an approximation for that tangent line. We can say that y is approximately 3. Okay, whoa, sorry about that. And now we need to update our slope again, because we're going to have a new tangent line with a new slope. So 4 times 0.5 squared plus 3. That's kind of nice because 0.5 squared is 1/4. 4 times a fourth is 1. So this gives us a slope of 4. So now we're going to write a new tangent line, or a new line equation, I should say. Y minus 3 equals 4 times x minus 0.5. The next example here, something that you might see on a BC exam, we have that the function f is differentiable for all values of x. In fact, here is the derivative graph, so this is f prime. We're given the initial condition that f of 0 is 6. We don't see f of x, but we know that its value is 6 when x equals 0. And f double prime of 0 is 1/4. So how would we interpret that? That would mean that the slope of the tangent to this is 1/4. So it's like going upwards very, very slowly there at 0, something like that. Now this part is only going to come into effect when we look at the further application of a MacLaurin or Taylor polynomial. So surprise incoming in just a moment. And again, we're given a portion of the graph of f prime. We're also told that the bounded regions R and S have areas of 1/2 and 5/8. So 1/2 is obviously contributing negative value since it's below the x-axis. And I might even draw these lines in red. So that's, contributing negative value just to indicate that. Now let's look at part A. Part A wants us to use Euler's method. Now instead of plugging in points to the derivative equation like we were doing in the last example, we have a graph of the derivative. So we just have to take values straight from this depending on what x is. We want to use Euler's method with 4 steps of equal size to approximate f of 2. So let's get this sort of chart down, but let's also list the x values we're going to need along the way. So we're going from 0 to 2 in 4 steps. I think it's pretty obvious, do some basic arithmetic, that we're going to need to take step sizes of 0.5. 4 steps of size 0.5 will get us to x equals 2. So we're going to have to update our tangent line quite a lot. Y equals f of x. And then we have, I guess we can just say f prime. It's the same thing as dy dx. All right, well, let's get started. We know that f of 0 is 6, so that is helpful. And we know that the value of f prime will always be found on this graph, okay? So for this example that we're doing, we're always going to reference the graph to get f prime's value. So f prime at 0, well, that's just 1. So that means that the equation of tangent line here is going to be y minus 6 equals 1, x minus 0. Well, that's pretty easy to do. So that means that y of 0.5 is going to be, or I should say f of 0.5 is going to be approximately 6.5, because 0.5 and then plus 6. All right, that gets us a little bit closer. Now we're going to use the graph of the derivative again to see what's the derivative at 0.5. So the value at 0.5 looks to be 2. So we're going to use a slope of 2, and we're going to write a new equation of tangent line. Y minus 6.5 equals 2 times x minus 0.5. And so we say that f of 1 is approximately 2 times 1 minus 0.5. That's just 0.5. So we should expect these steps to be 0.5 every time. That is the step size. Okay, so we're really just multiplying 0.5 to the derivative every time and then adding the previous y values. That's really not too bad at all. 2 times 0.5 is 1, plus the previous y value is 7.5. So we see that as the derivative is a larger value, of course, we make a larger jump. As the derivative is a smaller value, we make a smaller jump, right? Derivative of 1 led to a jump of 0.5. Derivative of 2 led to a jump of 1. Now let's take a look at f of 1.5. Sorry, f prime of 1, that's what I mean. That's down here at negative 2. So we're going to say that the slope there is negative 2. And so the equation of our tangent line there is going to be y minus 7.5 equals negative 2 times x minus 0.5. And then when we try to approximate f of 1.5, this is going to become negative 2 times, again, 0.5 is the step, plus the previous value. So this is going to be back to 6.5. Interesting. Let's find the new slope there at x equals 1.5. Look at the graph of the derivative, and it looks like that value is, whoa, that value is 5. So we get quite a steep slope at the end there, slope of 5. And let's make our final tangent line. This is going to be y minus 6.5 equals 5 times x minus 0.5. So when we approximate y equals f of 2, this is going to be approximately 5 times. You know the drill. The step size is 0.5. Oh, and whoops, this is not 0.5, and this is not. It should be x minus 1, and this should be x minus 1.5. I got into a bad habit of just putting 0.5 in there, and that almost cost me. Okay, so this is going to be 5 times 0.5 plus the previous y value. So this is giving us 9. So we can say that f of 2 is approximately 9. Okay, so Euler's method is a little bit tedious. If you increase the step size, then you get a less accurate prediction. Because if you think about it, again, let's use the analogy of like someone who's blindfolded and you're giving them instructions on how to like proceed along the curve. If you have them take really, really long steps, you're going to get further and further off quicker. If you were to take little tiny baby steps, if I took these little tiny baby steps and updated it as I go, see how I can hug the curve pretty well with these straight lines? Because I'm updating it frequently. If I use one really big line at first, even once I update it, it's going to take longer for me to get back to where it's actually supposed to be, right? Because I'm never able to like go backwards. So it's always recommended to have a smaller step size if you want more precision. Of course, it requires more calculations. There's a trade-off. You can't have it both ways. You can't have it be less calculations and be more accurate. That's what integrals are for, so that we can get the exact function. Okay, let's use a tangent line approximation at x equals 0. And so this is going to kind of illustrate the effectiveness of using small step sizes, because we use the step size of 0.5 to get all the way to x equals 2. But if we just used a single tangent line at x equals 0, you might remember that that tangent line is written y minus 6 equals 1 times x minus 0. If we use this tangent line to approximate, we would say f of 2 is approximately 2 plus 6, which is 8. Now that's not terribly far off, but it's not as close as we got with 9. What is the true value of f of 2? Now I'm not sure because we don't have an exact graph. In order to figure out what the true value is, I would have to be able to integrate this and use the fundamental theorem of calculus and say that basically the integral from 0 to 6 of f prime is equal to f of 6 minus f of 0. So I would be able to take this integral from 0 to 6 and add the initial value of f of 0, which is 6, and that would give me the exact value of f of 6. Now they do give us some bounded regions in terms of area, But unfortunately, they don't give us the area of Q. It would take some work to find that, and then we'd be able to use this. So let's make a second-degree MacLaurin polynomial. I know that MacLaurin polynomials are not exactly related to Euler's method, but Taylor polynomials and MacLaurin polynomials, they are approximation methods. They're just a little bit more sophisticated when you turn it into a higher degree polynomial. So the MacLaurin polynomial you might be familiar with is centered at 0. So this says that a function f of x is approximately its MacLaurin polynomial, which is going to be equal to f of 0 plus f prime of 0 times x minus 0, you just plug in the x value, plus f double prime of 0. Fortunately, we have that. We only have a graph of f prime, but we are given a value for f double prime of 0. So we're going to say that f of 2 is approximately f of 0, which is 6, plus f prime of 0, which is 1, times x, which is 2, plus f double prime is 1/4 when x equals 0 over 2 times 2 squared. So this is going to be approximately 6 plus 2 plus 1/8 of 4, which is just a half. So this is 8.5. This MacLaurin polynomial actually got us pretty close. It got us closer than just using the tangent line. So you can see the effectiveness of using a MacLaurin polynomial rather than just using a tangent line. Or if you're going to use a tangent line, update it with a smaller step size and you get a more accurate response. Okay, let's continue with another example here that gives us a graph. So this gives us a function that is defined, whose differential equation is defined as dy dx equals x times h of x. And here's the graph of h of x. So when we use our tangent lines, we're trying to create a tangent line and update it. The slopes that we get are going to come from this calculation. So we are going to have to do some calculations. We're given the initial condition f of 3 is -7. And a portion of h of x is shown here from 0 to 3. So I'm guessing we're going to start at, x equals 3. Yeah, because that's the condition given. And we're actually going to go backwards 3 equal step sizes to approximate f of 0. So when we go backwards, let's be careful about that. We're starting off at 3, and we're using equal step sizes. So that's going to be 2. That's going to be 1. That's going to be 0. And here we have these f of x values that we're approximating. And here we have these dy dx slopes that we're using for each of our tangent lines. So f of 3 is like -7. Our dy dx there is going to be 3 times h of 3, which is basically going to be 3 times -1. You see that? H of 3 is -1. And so we can make our tangent line as follows. Y minus -7 equals -3 x minus 3. Now we're approximating by going backwards, so we're going to plug in x equals 2. We're going to say that f of 2 is approximately -3 times -1. Notice that our step sizes are going to be -1, so that's what's going to go in this every time we use our tangent line. And we're going to, what is this? This is y plus 7, so we're going to subtract 7 on the other side. And we're going to say this is basically -4. So we can update our values, -4, and we can get a new dy dx value, 2 times h of 2. See how because the derivative comes from the graph, these two things are sort of done, they can be done simultaneously. They're kind of independent. In fact, I could write out dy dx for all of these already. This is 1 times h of 1. I don't need the y value for it. Okay, so 2 times h of 2 is going to be 2 times +2, which is 4. So we can approximate by saying y minus -4 equals 4. times x minus 2. I'm not going to make the same mistake last time. This tangent line is taken from the point 2, negative 4. So that means that f of 1 is going to be approximately 4 times, remember what this becomes? Minus 1. 4 times negative 1. And then this is y plus 4, so we're going to subtract 4 on both sides. And we get negative 8. So this is approximately negative 8. The slope at that point, 1 times h of 1, is 1 times 1. Pretty easy slope. They made it easy there. So this is going to be y minus negative 8. And if you're annoyed with calling it negative 8 minus negative 8, you can just put y plus 8. It's okay. It's going to be all right. Times x minus 1. Again, I'm not going to make that mistake. F of 0, therefore, is approximately 1 times negative 1, because that's what these always equal to. In this case, we're doing a step size of negative 1. And then we're going to subtract 8 on both sides. And this is negative 9. So we're going to say that f of 0 is approximately negative 9 by the Euler's method approximation. Okay, great. That was a quick little exercise there. Now here is the challenge problem of the day for sure, because we have a missing value k in our differential equation. They tell us that f of x is a particular solution to the differential equation given here, and we do have an initial condition f of 0 equals 2. So we're going to use Euler's method, and we're going to get that f of 1 is approximately 17 over 4 with 2 step sizes. So here's how that's actually going to work. If we draw our chart out, we want to solve for k, so if we draw our chart out, just trust the math of what we're given. Y equals f of x. And of course, the derivative equation, which is a little bit complicated. The derivative equation is k times x squared plus the y value. Well, the first point that we begin with is 0, 2. And so the slope there is very easy to figure out. The slope there is just going to be equal to 0 times k, which is 0, plus y. So this slope is 2. And we're using 2 step sizes to get to f of 1 is 17 over 4. So we already have some of the information. We're not looking for f of 1. We're using the fact that f of 1 is already discovered in order to predict what the k value is on Euler's method. So let's go ahead and write the tangent line. We're going to say y minus 2 equals 2 times x minus 0. And we know that the step size is 0.5 because we're taking 2 steps of equal size to get from 0 to 1. Now we don't know the y value here, but we can at least express this as, we can find the y value. We could say that f of 0.5 is approximately 2 times 0.5 plus 2, which is 3. So we know that this is 3, therefore we can get an exact value for the derivative in terms of k. So this is going to turn into k times x squared. I'll rewrite it in a moment. K times 0.5 squared plus 3, which just equals 1/4 k plus 3. Now, how would we write this in a tangent line equation? We would say y minus 3, that's the y value, equals 1/4 k plus 3, that's the slope, times x minus 0.5. And we know that we're approximating f of 1, so this is going to be 1/4 k plus 3 times 0.5, since the step size is 0.5, 1 minus 0.5 is 0.5. And then we're going to add 3, and we know that this is equal to 17 on 4. So how would this work? This would give us 1/8 k, I'm just distributing this 0.5, 1/8 k plus 3 over 2, however you want to call it, you can call it 1.5 if you want, plus 3 equals 17 over 4. Now what I'm going to choose to do is I'm going to choose to multiply everything by 8 because screw these fractions, right? We don't need them. You could also choose to multiply by 4 and that would still work. Let's multiply by 4 and see what happens. So we'll have 1/2 k plus 3 times 4 is 12 over 2 is 6 plus 3 times 4 is 12 equals 17. See how that cancels stuff out really nicely. So if we subtract the 18 on the other side, we get -1, and therefore k is -2. So this was an interesting application that you could see on the AP exam, the BC exam, because they're involving a constant, and BC problems really like to give you one or maybe even two constants that you have to solve for. And so this last example is not really a case of going through to find the last value. It's using the process in order to determine how you can find k. It's using the end result to inform us about something of the structure of the equation. All right, I hope you learned something about Euler's method here. It's very useful. And it often goes along with questions about polynomials, like Taylor polynomials, or even in this case, MacLaurin polynomial. Well, that's enough blab out of me in our investigation of using Euler's method to help you in Calculus BC. I'll see you guys next time in the world.